All right, so the goal of today is to do a brief review of RC circuits before we go into LC circuit. I'm sorry, RL circuits. So an RC circuit is a resistor and a capacitor. So let's just title this, yeah, there it is, resistor capacitor review. Now the reason I want to do this is because when we have RL circuits are very similar to resistor capacitor circuits, but they have a distinct couple of differences. So having a quick review of RC circuits should help us understand RL circuits. Now, the other side of this is why even bother, because we know RL circuits aren't going to be on the exam, so why should I even bother to learn this? Well, we could go down that rabbit hole as long as you'd like, except the truth of the matter is eventually you're going to college and I want you to be successful in college. So yeah, so there it is. You're going to have to learn things even if it's not on the exam. I know, weird concept and all, but here we go. So RC circuits, the thing about them that's important is the understanding that in an RC circuit, they still have to obey Kirchhoff's rules. And Kirchhoff's rules, even in a single loop like this, state that the sum of the voltage drops in any closed loop through an RC circuit has to be equal to 0. So let's go ahead and state that we have an EMF, there's a capacitor and a resistor, and that in this circuit is some amount of current. Now, I know it's been a couple of months since we've done this, but the point of this exercise is to remind us why we use Kirchhoff's rules in this way and how they are used to determine how the circuit behaves over time. Now, this circuit is super simplistic. I didn't include any switches, I didn't include any extra resistors, nothing complicated. It's just a reminder, because tomorrow when I post the RL circuits, you'll understand why I'm trying to be nice and provide you with a simple start. Not that RL circuits are any harder, but inductors are a little more complicated in the way in which they react. So this is our refresher. Besides, you've been off for a week, you need a refresher. So remember, it's going to look like EMF minus voltage across the capacitor minus voltage across the resistor all equals 0. So there it is. It's that simple. If it was that simple, we'd be done. But we know it's not that simple. The truth is, the voltage across the resistor we would write as IR. Yeah, not so bad. Oh, that voltage across the capacitor. It's been such a long time. Voltage, capacitance, how do we even deal with that? Well, the definition of capacitance is charge per unit voltage. It's how much charge a capacitor will store with an applied voltage. So in the case of this circuit, the voltage across the capacitor will be the charge per unit capacitance. Weird to do that kind of, flip like that, because it doesn't make a whole lot of sense, but it does in the long run. So we're going to write it that way. So that's going to be Q over C, and we still have our EMF. Now, all we did was go through our circuit and using Kirchhoff's laws, find a way to write out what the voltage is across each of the circuit elements. And every circuit element deals with voltage differently. Now, that's a long-term issue. You guys who decide to go further into study will understand that no matter what circuit element you have, they all deal with voltage and current a little differently. Kirchhoff's laws always work in all circumstances. So now that we have that, our goal here is to write this as a differential equation. The recognition that Q and I are related. Just a brief reminder, I is dq dt. And as we just saw, palm recognition on the old iPad, not the greatest. So that's dq dt. There we go. So now we can rewrite this equation as a differential equation. So we'll get the EMF minus, and I'm going to write the 1 over C out front so that I can put Q right there, minus I, which is R times dq dt, and that equals 0. There's our differential equation. So this tells us how a RC circuit will be charged. So let's go ahead and take this to another screen where we have a little bit more room so we can do a little bit of the mathematics. Now, I know you guys, love the mathematics part, but the truth of the matter is we need to see the mathematics part. So here we go. EMF minus 1 over CQ minus R times dq dt equals 0. Here we're going to just do simple, straightforward separation of the derivative. So we need to get the dq dt by itself. There's a whole lot of stuff here in the way, but none of that really matters. We still have to get it by itself, so we're just going to move this whole term to the other side of the equation so that we get E minus 1 over CQ equals R times dq dt. So to separate our variables, the reminder to all of you is that we need to get anything with a q in it on the same side as the equation as dq, and anything with t in it on the same side as dt, but there is nothing with t. It's all about q. So we're going to separate our variables by multiplying both sides by dt, and then get everything with q in it on the same side. So it's not a whole lot, but basically we're going to have dt on the left side by multiplying both sides of our equation by dt, and have r over E minus 1 over CQ dq. Now this looks like a mess, and the truth is it is a mess. But our goal was to get everything with q in it on the same side as dq, and everything with t in it on the same side as dt. And we've successfully done that. But we now have to find a way to integrate this and to get an equation that is based on t and, an equation based on q in terms of t. So that's our goal now. So although there's not a lot of good reasons to do some of the things I'm going to do, in the long run, they do help us out. For example, I'm going to multiply both sides of this equation, the right side, by c. That's going to put RC in the numerator and epsilon c minus q in the denominator. Part of the reason for this is a long-term knowledge that our whole equation is actually based on RC, and E times C actually has a benefit in the future in that it's going to be the charge on the capacitor. So by doing this, we're kind of preparing things for the future. It's not necessary to do that, but it does make the math a little bit easier to look at. Also, I'm going to multiply both sides right now. Actually, I don't have to, but I'm going to multiply both sides by 1 over RC. That's going to have negative 1 over RC on the left side with dt, and 1 over EC minus Q on the right side. A lot of textbooks do it this way, and the point here is that in the future we know we're going to raise both sides to a base of E to get rid of a logarithm. So we're just getting this out there in front of that T nice and early. Okay, so let's go ahead and fix this up a little bit. I'm going to move everything up a little ways so that we can kind of focus and do what we need to do. We're going to integrate both sides. So I'm going to put an integral symbol on both sides, and then I'm going to decide how I want to integrate. The left side is all about t, and remember, we want our integrals to have common variables. What I mean by that is, what is going on at time 0? Well, at time 0, the capacitor, that's Q, is uncharged, so the capacitor has 0 charge. In some time in the future, T, the capacitor is going to have some kind of charge, Q. And I know that bothers a lot of people that I've got little q and little q in the dq and t and little t in the dt. The idea is to remember that the t's and the dt's are all representing variables. We are trying to create a function, and that function is about what happens to q over time. So this q is related to a q in the future, and this t is related to a t in the future. That's different than dq, which represents a small differential, a small change in the value of q, and dt, which represents a small change in the value of t. Either way, the left side of this is super easy to deal with. The left side of this is just going to be 1 over RC times t minus 0. That's no big. The right side is so not happy. It's so complicated. It's so, we're gonna have to do one of them crazy, I don't care about it kind of calculus things. The favorite one here is that we're gonna have to do u sub, and I know you guys love u sub. So my u sub is gonna be u equals EC minus Q, because that's the appropriate u sub here. And to do that, I need to take the derivative, so du equals minus dq. So now that I've got my u sub ready to go, this is going to be the integral of 1 over u times negative du. It's not a huge deal, but remember, I kind of ignore the limits right now because I know in the future I'm just going to plug back in my u sub, and my u sub has different limits than u does. Mr. Bright, Mr. Bashir, they're going to be all mad about that because they want you to put in like the actual limits that now match up with u. But, you know, I play hard and fast with the rules here because physics doesn't care about calculus. They just want to use calculus to get their job done. So let's go ahead a little bit into the future. So 1 over RC times t equals, and here we go, we have the natural log of, and I should put u here, but I'm just going to be, forthright with you and say u is equal to EC minus Q. But then I do have to put in my limits of integration. So let's make that, natural. It's a natural log, but it's of the absolute value. And calculus folks are all super cynical about their absolute value. We know this has got to be greater than 1, but calculus folks are always worried that it's not going to be. So that's why we've got those absolute value bars. But I still need to put my limits out there. That's going to go from 0 to Q. And so there we go. There's that negative sign, that pesky negative sign I didn't deal with. It's right here. How about I put it right there? That'll make everybody happy, right? Yeah, well, I'm happy, and that's all that matters. So we're kind of done here. I do need to make sure that we've plugged in both of our limits there. So natural log of EC minus Q, whoops, that was almost a parenthesis, but I gotta have the absolute value, minus natural log of, I gotta put the 0 in for the Q, so I'll get just EC. I still have my absolute value. So there we go. Yeah, the right side, we know we can write this as a quotient. So I'm going to go ahead and do that. EC minus Q over EC. I'm leaving those absolute value bars in there. That way everybody's happy. The right side, the left side is still 1 over RC times T. Now, that's a lot of work, and I agree with you. Let's get all the way up there. It seems like a long way to go just to get this, but here we go. At this point, we want to get rid of the natural log. So we're going to raise both sides to the base of e. So base of e, and that's going to be minus t over RC. Yeah, I know. I made the RC super small, but that's the way it goes. And the other side is just going to be EC minus Q over EC. Yeah, I'm stripping away those absolute value bars because that can never be negative. Why am I worried about it? And truthfully, I'm not. So our job now is to solve this for Q. And there's a couple ways to go about it, but probably the best way is to go ahead and multiply both sides by EC, and I'll get EC, and I know I'm calling it E, and there's a lot of E's here, but that's the way it goes. And I'll get the that thing on the other side. So I want Q by itself, so just a little bit of algebra, and I've got this jobby right here, and I factor out that, and I get my expected answer, which we've done a couple times, but here it is. No big. This we know represents the value of the capacitor when it's fully charged. So, that one will get out of the way. Let's get them out of the way. There we go. So the value of the capacitor when it's fully charged. This is Q as a function of T equals Q max. That's right. I'm going to put the big old Q there. Why? Because it's Q max. It's the fully charged capacitor times 1 minus e to the negative t over RC. All right, so there we go. We've done it again. It took us a whole 17 minutes. I know it's a long time. But we have a function here that describes how the capacitor gets charged over time in an RC circuit. We use Kirchhoff's laws to do so, which create a differential equation. We use that differential equation to figure out a function of Q in terms of T. And because we have a relationship between Q and current, I, we can always take the derivative here and figure out what the current will be. I encourage you to do that, but I'm getting close to my absolute value of time here. But also, we can divide both sides of this by the value of the capacitance. And if we do that, we get a different function, which is going to be, dare I say, the voltage across the capacitor. It's going to be equal to the total EMF over C times 1 minus, there we go, 1 minus e to the minus t over RC, which tells us that the charge on the capacitor and the voltage on the capacitor are identical in the way in which they charge. But if you go ahead and try and do this differential, which I really encourage you to do, it's an appropriate differential to do, you're going to get the function of the current. And when you do so, Q times 1 is going to be a constant. That goes away. And so when you're taking your derivative, you're taking the derivative of negative e to the minus t over RC. And that's going to give you, without a whole lot of proof, Q max over RC times e to the minus t over RC. And this is great because this is actually the EMF divided by R, which is the max current you would get when you had no capacitor at all and just a EMF and a resistor, but that it immediately decreases over time. So you could actually write this as I max e to the minus t over RC. Now, this was a review, and the goal of this review was to get you prepared for what inductors are. So tomorrow we're going to talk about inductors. Good night.